last class, and we started this section on common functions and figuring out how to draw graphs that maybe look the same, but maybe are like a transformation of the other one, okay? We went through, I think, 8 common functions that I told you you had to know how to draw. And what I mean, know how to draw, I mean, know their basic shape. So know if it's like a horizontal line or a parabola or a V shape. Do you need the notes? Okay, good. Okay, and so you have to know the shape. That's one thing I'm looking for. The second thing I'm looking for are important points. So any point that maybe exists at 0, 1, or -1. So those sort of points. And finally, I wanted you to know any asymptotes. So if it's a function like 1/x or 1/x², I want you to draw them with dotted lines. So wherever the asymptotes are, I need you to know that. Okay, that will come in handy during our quiz. Okay, so you have to memorize how to draw these graphs, or at least know how to find them by plotting points. And now we're gonna look at other types of graphs that look very similar to the common functions, but they're kind of shifted a little bit. Okay, so if you flip to the next page, we have our first transformation of functions, and we call this the vertical shift. Okay, so I know this is written very abstractly, but let's just say we have this graph y equals f of x. Okay, and I take my function that I already know how to draw, and I add something to it. So I take this function and I just tack on +4 or +5 or +6, okay? What this means is we're gonna take the original graph and we're gonna shift every single point up whatever many blocks that I added to it, okay? So whenever I add something to a graph, I'm shifting it upward. What happens, do you think, if I subtract something? Shifts downward, right? So it doesn't have to shift up. If I'm going to make a little note here, if C is negative, then that means you shift down, right? Okay. So little example here. We have the graph x² - 4. Let's say I wanted to graph this. Already looking at the graph, what do you think, which graph do you think I'm actually shifting down looking at this equation? What do you think, like, the common function on the first 2 pages I'm working with here? Not -4, x², right? If I look at this, x² is a big hint because I have a graph that says x², right? And I know what that graph looks like, okay? What's the shape of that graph? For U or parabola, right? And we know that the 3 points from our memory, right, are 0, 0, -1, 1, and 1, 1. Okay. And I know that this graph has a U shape. Okay. So I know it sort of looks like this. Okay. This is my original graph, right? So I'm going to label this original graph. And this is the graph of x². So I've taken x² and I've just subtracted off 4, which means I'm going to take each of my points. So for example, 0, 0, and I'm going to shift it up or down. Where am I going? Down, good. So I'm going to shift it down 1, 2, 3, 4 points, right? So the point 0, 0 becomes 0, -4. Okay. Same thing with -1, 1. 1, 2, 3, 4. That gets shifted down here. And then the same thing goes with 1, 1. So I'm going to shift that one down 1, 2, 3, 4. And that point becomes here. Okay. Once I have my 3 points, I can connect them in the same shape. And it looks like we have another parabola that is very badly drawn, but looks about like this. Okay. So any questions on shifting up or down? I think this is pretty easy. I know I wrote very fast here, so I'll leave this up for 2 seconds. Let's talk about a different type of shift. Okay. So another abstract sort of situation here. Let's say we have the graph y equals f of x, okay? And instead of adding, oh, sorry. Instead of adding or subtracting to the entire function, we have f of x minus c, okay? I think, did Grace come in? Do you need the notes from last class? No. Oh. Okay, and this is different, okay, because let me put both of the vertical shift and horizontal shift next to each other. Okay, in vertical shifts, the definition said, I'm going to take f of x and I'm going to add c to it, okay? With a horizontal shift, I'm not adding anything to the original function, I'm subtracting something inside the function. So I'm subtracting something to the x value in here, okay? Now I know that sounds really abstract, and if you don't see it yet, I think the next example will show the difference between a vertical shift and a horizontal shift, okay? But basically what this does is when we subtract something from x itself and not the entire function, the graph is going to shift horizontally to the right, okay? And I know it seems counterintuitive because when we subtract, something goes to the right, okay? What happens, do you think, or what do you think happens when we add something to x? What direction is it going? Not up, to the left, right? So opposite of right is to the left, right? So when we subtract, goes to the right, add goes to the left. Okay, let's put this together. Example 2, we want to sketch the graph of t of x equals the absolute value of x plus 3, okay? Now I want to make a very big point here, okay? This is different, okay? This is a different question than this question. So if I were to ask to graph this function, t of x equals the square root of x plus 3, something different is going on the right. What's happening over here? What sort of shift is going on the right? A vertical shift, right? Because the 3 is being added to the entire function, the absolute value of x. Over here, the 3 is being added to x inside the function. Do we see the difference? Okay, so over here, this is a horizontal shift. Over here, this is a vertical shift. Okay, so before you even talk about where it's going, what is the original function I am shifting here from the first page? Perfect, the absolute value of x. And a big hint is that we have absolute value signs. Good. Okay, so of course you can peek back at your notes and see how to draw this, but I'll give you the 3 points that we need. 0, 0, negative 1, 1, and 1, 1. And what does the absolute value graph look like? What shape does that have? A V, good. So that's shaped very similar to a parabola, but the lines are straight. Okay. So looking at my function, it says I'm adding 3 to x inside the absolute value signs. Am I going to the right or am I going to the left? Not the right, the left. When we add in here, it means we're going to the left. If we're subtracting, we're going to the right. I know it seems counterintuitive, but it's actually the opposite of what we actually think. Okay, so I'm going to take each of my points. I'm going to shift them to, I'm going to shift them 3 values to the left. Okay, so I'm going to start with 0, 0, and that becomes negative 3, 0. I'm going to take my negative 1, 1 point, shift it 3 points to the left to get negative 4, 1. I'm going to take my 1, 1 point and shift it 3 points to get negative 2, 1. Okay. Once I have my points labeled, I can create the shape again, and it looks very similar to the last graph, except it's shifted to the left by 3. Okay. Any questions so far? Okay, good. Let's go on to the next example. We're actually going to put together vertical and horizontal shifts and see what happens to the graph when we combine them. Okay. So this example, we have the graph of q of x equals 1 over x minus 3 plus 1. Before I talk about the shifts and whatever's going on here, thinking about this, what is the original graph I'm shifting here? I hear asymptote, but like which graph am I doing? Because there's two graphs that have asymptotes. Yeah, it's 1 over x. It's not 1 over x squared because there's no squared in here, but 1 over x is the one that we're looking for because we do have a denominator. So the original function is the 1 over x function, okay? And from our previous work yesterday, we knew that the 1 over x function had two asymptotes, and that was the x and y axis. And I said, you can just draw them using dotted lines, but you definitely have to mark that they're there. Okay. There were 2 points on the 1 over x function. It was 1, 1, and -1, -1. And the 1 over x function was pretty cool because once we drew those points, it's pretty obvious what the function looks like because the graph never touches the asymptote and it gets really, really close to it. Okay, so this graph looks like this. Okay, so that's my original function. Let's write out what's actually going on with our shifts here. Okay, we have x minus 3 and a plus 1. Let's start with the x minus 3 here. Do you think that's a horizontal shift or a vertical shift? The x minus 3, is that a horizontal shift or a vertical shift? Horizontal, and why is it horizontal? Yeah, the -3 or the -3 is attached to the x. We're not subtracting 3 from the entire function here. The 3 is attached to the x, right? So because the 3 is paired with like the x minus 3 on the bottom of the of our 1 over x function, we're actually doing a horizontal shift. And that's what that 3 is telling us to do, okay? Since I'm subtracting 3, am I going to the right or to the left? To the right, right? When we subtract, we are horizontally shifting to the right. To the right. Okay. Now we already did the horizontal one, so it's pretty easy to figure out what 1 is. Is 1 a vertical shift or a horizontal shift? Vertical, right? This 1 is being added to the entire function. It's not inside the 1 over x function. It's kind of tacked on to the side. So 1 means we're doing a vertical shift. And are we going up or down? Good, we're going up because positive means going up. Okay, so very similar to what we've been doing here. Why don't we take each of our points and plot where they're going? Okay, I know that what if I start with -1, -1? Well, I can shift it 3 values to the right, and I can shift it 1 value up. Okay, so this point would go, gosh, 1, 2, 3, wait, 1, 2, 3, right here. Okay, I can also move the 1, 1 point 3 to the right and 1 up. So it becomes 4, 2. Okay, what do you think happens to the asymptotes? Yeah, it shifts with it. Now, if I start with my vertical asymptote, I can shift it 3 values to the right, but shifting it up doesn't really do anything to it because it's already a vertical line. You can't shift a vertical line up anymore because it's already a vertical line, okay? So I'm just gonna take that vertical line and shift it 3 to the right. So that vertical asymptote is going 3 to the right Okay, same thing with the horizontal line, but I can't shift a vertical line, or sorry, I can't shift a horizontal line 3 units to the right because it's already a line and it takes on all the values left or right. Okay, so I'm just going to shift this line 1 value up as well. Okay. So same thing as we've been doing with the functions, except you're also shifting the asymptotes as well. Okay. Once we have our points drawn and our asymptotes, we can complete the shape of our graph. And it looks like this. Okay. So we're just combining our knowledge of horizontal and vertical shifts together. Okay. Right here. So this time we have a function, and it's x plus 3 squared minus 1. Marissa did a great job of showing this shift. Marissa, why did you draw the graph of x squared here? Yeah, right. There's a square in it, which is giving us the hint that the original function is x squared. Okay. Okay. Then Marissa was like, okay, I need to go left 3 and down 1. Why did you make that decision?
Because you were adding 3 to x and then that 3 to the right. Subtracting
Good. And then finally, I think what Marissa did, she took all her points and shifted them left 3 and down 1 like this. And then finally connected the points in a parabola. Okay. Any questions on example 4? All right. I think we're all good with sketching functions that are shifted horizontally and vertically. Let's make it a little bit harder. All right. Flip our page. Here's where things get a little bit more complicated, I think, at least to me. And this is where we go into our vertical stretching. Okay, so we don't just have to shift a graph, we can actually stretch and compress a graph, either horizontally or vertically. So let's start with the vertical stretch. Okay, so let's say we have a graph, f of x, okay, and we take our function and just multiply it by something. So like if I had x squared, I would multiply it by 3, or if I had 1 over x, I would multiply it by 2, okay? Okay, this means that our graph is either stretched or compressed, and it actually depends on what sign or what value of the number the function is multiplied by, okay? If our number is multiplied by, or if our function is multiplied by something that's bigger than 1, it's actually going to stretch it. So it's going to make it a little bit more thin. Imagine taking our graph from the top and bottom and stretching it up and down. Okay. If the number is less than 1, we're actually compressing it. So we're kind of like moving it, moving the top and bottom towards each other and making the graph a little bit wider. Okay. Now, you don't actually have to know the difference between stretch and compress. You don't have to memorize that if you don't want to. I just want you to be able to take a graph and be able to stretch the points and compress them in the way that I'm going to show in this example. Okay, so let's start with this graph here. We have the graph 4x squared. Okay, and let's just draw out what this might look like. Okay, looking at our function on the first and second page, what function am I originally going to draw first? X squared, right? The original function here, and let me zoom in here real quick. Original function is going to be your x squared function because there's a square. Okay, so just drawing the points of these function of this function, it's going to look like this. Actually, that's not very good. Let me do this. There we go. Okay. Now, from here, you can either think of this as stretching or compressing, which I think is a little bit harder, but if you have a different way of doing this, that's fine. What I like to do is I'm going to take the important points of this graph, okay? And I already have them plotted on my graph, okay? I know that the 3 important points on this graph are -1, 1, 0, 0, and 1, 1. Now, what this function is doing is it's taking my original values and it's multiplying it by 4. Okay. So let's see what we can do here. I'm just taking my y values and multiplying them by 4. Okay. So what do you think negative 1, 1, what do you think that 1 is going to turn into after I multiply it by 4? 4, right? So after stretching the graph, this is going to turn to 4. After stretching the graph by 4, what do you think 0 is going to turn to? 0, good. And then 1 is also going to turn into 4. Okay. So now I have a new set of points, x and y, where negative 1 is now mapped to 4, 0 is now mapped to 0, and 1 is now mapped to 4. Okay. Well, I can plot these points. Negative 1 goes to 4, 1 goes to 4, and 0 goes to 0. Connecting these points together, the graph kind of looks like this. And thinking about our vertical stretch, it actually does look like I'm vertically stretching my function because 4 is bigger than 1. Okay. Any question on example number 5? All right. Why don't I let you do example number 6? Same sort of deal here. We're taking x squared, but now I'm going to multiply by 1/4 instead of 4. Question to example number 5, but instead of multiplying by 4, we multiplied by 1/4. Grace did a great job of drawing out her parent function, x squared, which is exactly why we drew the same parent function last time. And before I ask Grace to explain her method here, I'm actually going to write down the same chart that I used last time just to keep it a little consistent here. Okay. So we have 3 points on our graph. We got negative 1, 1, 0, 0, and 1, 1. Okay. And since I am multiplying all my y values by 1/4, these guys are going to change to 1/4 times whatever the value is. So 1/4, 0, and 1/4. Now, I think I just explained it for you, Grace. I guess you don't need to say anything now. But Grace did a great job of plotting her points. And because our factor is less than 1, we're actually compressing the graph now. So imagine taking the top and bottom of the graph and kind of moving your hands closer. This graph is getting shorter and wider, right? Okay. Any questions on example 6? Good. All right, so if we flip our page over, okay, we have a different type of shift now I want to talk about. We did vertical shifts and compressions. There is a thing called horizontal shifts and compressions, but I'm not going to go over that in this class just because if you can shift something horizontally, you can also do it vertically. So we're just going to work with the vertical there. Okay. Next, let's work with reflections. Okay. So there's actually 2 types of reflections. There is a reflection about the x-axis and then a reflection about the y-axis. Okay. Now, very slight difference between the 2. Okay. Reflections happen when we have a negative sign floating around. Okay. So the negative sign can either float outside the function, so it can be attached to the entire function, like negative x squared or negative 1 over x. Okay. We can also have a horizontal, or sorry, a reflection about the y-axis. And here the x or the negative sign is attached to the x. It's not attached to the function. Okay. So I want to go over this a little bit and have you see the difference between reflecting about the x-axis and y-axis. Okay. So here's example 7. I want to sketch the graph of negative the absolute value of x. Okay. Before we even do anything, what graph am I starting with? Yeah, absolute value of x, right? Because there's absolute value signs in it. That means we should probably use an absolute value function to start. And that one looks like the straight line function, almost looking like x squared, but the lines are straight. Okay. Now, let's look at the placement of this negative sign. is the negative sign on the outside of the function or on the inside? It's on the outside, right? So this is on the outside of the function. Which means, are we shifting, or are we reflecting about the x-axis or the y-axis? X-axis, good. So we're going to reflect about the x-axis. Okay, now I want to show you what this would look like if this was a different type of question. Okay, so make sure you write this on the side so you don't get confused with this example. But in this alternate example, okay, so alternate example, if I gave you this question here, g of x equals the absolute value of negative x, what am I reflecting about now? The y-axis, okay? So on the right, we have the negative on the inside of the function. On the left, the negative is on the outside. So this is on the inside, and we're reflecting about the y-axis. The actual question that we're doing, the negative is on the outside of the function, which means we're reflecting about the x-axis. Okay, so how do we do this? We're just going to pretend that the x-axis is a mirror, okay? So imagine that the x-axis was a mirror and you wanted to see what was on the other side, okay? Basically what you do is you take every point on the other side of the mirror and you flip it over the x-axis, okay? So the distance between this point and the x-axis is going to be the same as the x-axis to the other point, okay? So this point is just going to be flipped over the mirror like that, okay? This point is also going to be flipped over the mirror the same distance, okay? How do I reflect the point 0, 0 across the x-axis? The middle point. What happens to that one? Just stays the same, right? If you're on the mirror, if you reflect across it, you're still on the mirror, okay? So that stays the same. Okay, so reflecting about the x-axis, we did all the points, and all we have to do is connect our lines in the same shape of our parent function. Okay. Any questions so far? Sounds good. Why don't you try example 8? Little different type of function that we've been working with today, but I believe that you can do this one pretty well. So going over this example, we have the graph of the square root of negative x. Why did you choose the graph that you chose, Ainsley? Mm-hmm. Nice. So you started with the square root function. You knew you had to flip across the y-axis because the negative was on the inside, okay? Now, I do want to just give an alternate example just so you can see the difference. Okay. What would the function look like if it was asking us to reflect across the x-axis? What would that function be? Yeah, it'd be negative square root of x, okay? So what I just wrote on the right-hand side, this would tell us to reflect across the x-axis, okay? This function, the negative is on the inside, so we're reflecting across the y-axis. Okay, so it all depends on where that negative sign is. Is it close to the x or is it away from the function? Okay. Any question on these examples here? All right. I'm actually gonna wait a little bit to finish this because I think we have a quiz review to do. And this quiz review isn't that bad. It is literally